begin. So today's review lecturer is Monica Kang from CALTECH, and Monica will be talking about interdimensional holography, bulk reconstruction, relative entropy, and operator algebra. So please.
Thank you so much for this kind opportunity to visit Cambridge and this beautiful building. And for the wonderful opportunity to give a talk about my own works in review format. So granted, it's in review format, meaning I won't be able to go as much detail into individual topics. So if you're lost, please do raise an app. I'll try my best to answer I can as possible. And I just flew in from America and the East Coast, so I'm practically not awake at the moment. So if I give you an answer that is not good enough, please ask again in the afternoon. I'll probably give a better answer. So today I'll talk about infinite dimensional holography, meaning holography would take it in the context of infinite dimensional Hilbert spaces that I've been pushing for the last few years. And overall, the real things that you're going to understand through this context will be bulk reconstruction, relative entropy, and operator algebra. And these will be based on, of course, I'm not going to go over all the individual things, but there'll be a lot of different little things that I have used throughout in these papers with my beautiful set of collaborators all over the world. Once again, it will be heavy on more, it's a good way to say it, more algebra side, as the title really suggested. So if you're confused, please stop me. I will answer as much as I can. So as the title suggested, and I just noted, I will be using throughout as the toolkit as operator algebra. So you should probably first then ask me, why am I using operator algebra as a particular toolkit or the topic of interest to consider? It's because throughout years as a theoretical physics, it's usually very difficult to work directly with fields necessarily, though it gives a lot of good toolkits to compute explicitly, because field itself is not really like an invariant notion of a quantum field theory. So for example, like in Chern-Simon theories, we had to work with not invariants like Jones polynomials to compute the whole set of correlations, or we come up with central charges for a generic part of CFD. So it's like a good thing to have as an invariant notion that can attack the problem in physics as more holistic together. And the same notion of it, algebra of operators are more of an invariant notion of a quantum field theory, in a sense that, for example, it'll understand causal commutativity and many other things. So that this will be more capturing physical information that is encoded without depending on a particular choice of a field description or any like set of a given little bit of the field descriptions. So with this context, I'm going to utilize this operator algebra perspective to understand our holography structures. So the one in the left is a beautiful picture I took in a local museum in Korea near my hometown. I think it really captures what holography means, and this is how I'm going to really address algebra with it. So the bulk in this little one-dimensional higher space is very complicated and complex, but it projects down onto the boundaries. So these operations with algebra is called projectors, and it literally takes as a projection, and that can be taken from algebraic operations like what you see in the as a shadow, while it's keeping a lot of structures intact. As like the woman is actually holding the space-time, it'll contain all those structures. It'll be encapsulated in the structure of algebra. And this is what we're going to really address today and try to understand how the structure can be understood from this perspective. And from more modern recent decade, you have learned that there's error correcting properties arising in the context of holography. And through this algebraic approach, we'll understand these error correcting property naturally appearing. So like we check an Ege surface, that's a delimiting surface, and many other things. We'll actually address them in this format and how that will be effective to provide something new that we did not know before.
So what is the member diagram of this?
That would be great. So really more of a physics-friendly way of capturing from the beautiful photo is really the following. The holography will be taking the notion of mostly the HKLL protocols here, but not as much as in state paradigm. It will be using operator paradigm here. And I'm going to take the von Neumann algebras in variety of many different contexts, which first initiated by Hawk and with the construction by Wissenbaum and Wickman will be mostly used throughout the talk. And the quantum error correcting properties will naturally occur that will match with Elmhirst-Dunn-Harlow and Dunn-Harlow-Wall type of formalism, and a little bit more beyond, as we're taking it not in the finite dimensional perspective, but very explicitly infinite dimensional over space perspective. So what's the operator picture we know from the holography? Well, so we have the bulk and boundary reality, but the scale is a little bit different. So when we have local bulk operators, they can be provided as the boundary operators, but not quite local. It will be actually smeared over entire spatial slice or a compact spatial subregion. So what we really need to also address is what are these smearing functions and what those function space really give rise to. And that's really the essence of understanding from operator algebraic perspective, because I personally don't know how to deal with most analytic structures because they're very hard. And deal with it by making it more equation solvable algebra perspective. Because I mean, that was the whole beauty, in my opinion, when you're addressing more simple CFTs or TQFTs by having versorial algebras. It's like the similar structure in mind, but it's more real-based structure, not complex-based structure. So as you're learning recently a lot throughout, we have the error correcting property. So in this context, we're going to use operator algebra as von Neumann algebras. Then these local bulk operators that we check will be then expressed in the code subspace of the bulk of the code subspace of the physical Hilbert space of the boundary conformal field theory. So in this context, we have emerging error correcting structure and many of the other contexts, but most important thing that we'll utilize today is that it's going to give rise to root check and surface, or more generically quantum external surface. And under that such delimiting purposes, we'll have bulk reconstruction, meaning that all the information in the boundary will be encoded in the bulk. So that way of putting it together is then we'll have a map between this bulk and boundary as a holography, and we'll have a complete recovery of the information that we can throughout. So it's redundantly encoded between boundary and the bulk. Yeah. So in this context, if we have a complete entire thing encoded redundantly with another, is a complete recovery. And when you have less, that will be called approximate recovery. And both of it we'll address today in this paradigm. So as I was keep telling you, then I'm going to get these through the operator algebra throughout the talk today. So what is the local operator algebra that we're going to really utilize? That's called von Neumann algebra. Despite its scary name, it's actually very simple. All it means is that it's a star algebra, meaning it has a Hermitian conjugate, like the ones in quantum mechanics, that its double commutant is exactly mapping back to itself. The commutant, double commutant means I did the commutanting twice. And commutant is a very intuitive name that exactly does what it does. It's exactly with the operators that commute exactly to one another like this and put them all together. That's the commutant. And most mathematical definitions are usually vague, but this, in my opinion, is one of the most intuitive definitions. So when it says double commutant maps back to itself, then the commutant itself will also have to share the same property. So in turn, that's also a von Neumann algebra. So in this paradigm, what we're going to have is we're going to have a particular von Neumann algebra, and its commutant is also a von Neumann algebra. And when you do it back to it, then it maps back itself. So we can always address the regular side and the complement side. So while most quantum gravity theories are done with the finite dimensional density matrices, so that we can explicitly have, density matrix and explicit operations done. Those are very different from generically infinite dimensional Hilbert spaces. So von Neumann algebra generically is categorized into three different types. It's called type 1, type 2, and type 3. And it's not very illuminating, but I didn't do that. So type 1n is the finite dimensional Hilbert space of dimension n. So that's the only one that we can always address everything entirely in linear algebra. So all the rest are then infinite dimensional Hilbert spaces. The first thing, the most naive one, n to take into infinite dimensional, then it's 1 infinity. That's the first type. And type 2 are the ones that's not quite infinite. So it's infinite dimensional, but it has some form of structures that preserve the linearity, so that you can have a still like a map that's a strong parameter 1 family, so it can be addressed as a trace, exactly identical. Then if you can do something like that as type 2, type 3 loses all those structures on top separately. So every von Neumann algebra have to, even if you don't use the definition of Hilbert space, it always admits the unique existing Hilbert space. You cannot define von Neumann algebra without it. Even if you follow the protocol without using Hilbert space, there is an implicit and explicitly derivable unique existing Hilbert space. So that is not different from Hague context at all. In fact, Hague is using in this particular definition of von Neumann algebras into the theories that he's utilizing, which is different from how I will going to utilize, but that is not addressed in this slide. In this slide, it's the most generic one. Hague is more specific part of this. Yeah, and there's 3 different definitions of von Neumann algebras, and they're all shown to be explicitly equivalent. And you can just take this as the easiest that I can give without giving the full jargon of math. They're actually explicitly equivalent, and it's shown mathematically actually reversible.
So what is I infinity like? What's to 1 to infinity 3 down?
I mean, I will, if you're curious, I can actually tell you the full explicit definitions after like in the talk is finished, but I'm not going to derail the whole talk defining the type 1 and 2 and 3 explicitly. The goal here is to actually use them, and it will not matter today because I'm going to take all von Neumann algebra to be generic today. If you're actually curious, really, like, come and ask me. I'll give you the full view of it. So the von Neumann algebras can be then used in the context of holography from utilizing these, but if you notice, these are for given one theory, one Hilbert space. So you have to use it for the ball theory, that's coupled to gravity, or for the boundary. So in this context, I'm going to deal with all the semi-classical limit of the ball gravity theory and the boundary form field theory. And then having those 2 separately addressed, then we're going to have explicit holographic map. So that it was mapping, if you remember from the previous slide, the bulk operator to these boundary operators with the smearing function. This is how we're going to address them explicitly. And the smearing function is also part that's inside the von Neumann algebras, which is a very important fact that you'll need to understand, because so the function space where the operators are belonging, because your operator is already grabbing from this bounded operator set of the Hilbert space. So that smearing function has to be already addressed to integrate over for where the operator belongs, like what we learned in the first quantum field theory textbooks. And these are for, yes.
So the first case, algebra
it's just coupled to gravity. Now, it's a semi-classical quantum field theory that I'm going to address.
Do you have a quantum gravity? In what sense that
So I'm going to first start with the complete. So that's actually a good question. So type 3 is the only one that actually gives you a continuous spectrum. And in this context, I'm actually going to address all types. It includes type 3 as well. But if you're considering a full explicit non-perturbative gravity corrections turned on, in that context, you'll have to get to it that you cannot explicitly necessarily be able to deal with that.
What is the language of a phenomenon algebra used when you talk about the theories that are well defined in the continuum?
Yes.
And gravity doesn't exist in the continuum.
Well, the continuum limit only also exists in type 3, right? Because it doesn't give you a spectrum to be continuous. Yeah, indeed.
So you're talking about something, I mean, if you want to be rigorous, you're talking about something that doesn't exist.
Well, how about we'll get back to this question, because I actually love this question. But maybe it'll be more enlightening, because I'm going to talk about non-perturbative gravity corrections included in the end. And I'll come back to answer your question. All right, and I don't have to do it. But I do use that space. Good. All right, and these are approaches in a variety of contexts. First, it was addressed by Reren, and thus it's called Reren duality sometimes. It's not what I am doing today, but it's the first paper that addressed an algebraic sense of holography. And Longo and Rara et al. Were introducing a lot of the concepts in the context of HPFT that I'm going to borrow as a language, but not in the same formalism at all for today. And these are utilized by all of our own higher energy theory people in many different contexts in modern times. So then first thing you should probably be curious about is how do we get the von Neumann algebra in a quantum field theory? And the most importantly, quantum field theory has a space-time, and so how do we really understand them in that context? So let's say we have U as some open region of space-time, then we can define some form of algebra by taking the algebra of the operators living in the open region of U. Let's call that some algebra A of. Then it's an associated local operator algebra that understands where the operator lives as a locality in the region of space-time and U. But of course, the operators are generically unbounded. And if you remember from von Neumann algebras, it has the bounded operators in the Hilbert space. So in order to get that, we have to go through then polar decomposition for all these, which will give you a partial isometry, and the self-adjoint positive operators, which are canonically associated to the full set of projections by spectral theorem. Then the von Neumann algebra that I'm going to distinguish by calling it M is the set of bounded operators. So then we have to generate it through this explicit outputs that you're allowed to have. And those are generated by partial isometries. And that was over there, the green that's associated into the operators now in M view. And all the set of all projections that we can get from the self-adjoint positive operators. So that combining them as a generator together is the way that we're going to get von Neumann algebras explicitly. And you can imagine you can deal with it from explicit functions and computing them. And these are how the procedures in practice to actually get it work. So in turn, the von Neumann algebra is, if I notice, it's M of U, meaning it really denotes the subregion where it lives on in the both in the theory of context, if I take it into bulk in the bulk subregion, or boundary in the boundary subregion.
Good question.
Yeah.
Partial isometry?
It's an isometry that's partially there. So it's keeping the partial part of the isometry. Now we're going to use these von Neumann algebras in the context of holography. So then how are we going to really associate them? So the bulk theory may be effectively described by the quantum field theory on a global ADS background, and or asymptotic ADS background. And for those, we're going to take it a semi-classical limit, so it'll be the quantum field theory that's going to be described as. And we're going to use a von Neumann algebra to describe the operators associated with the now covariantly defined subregions in the bulk. So that in turn, this covariant described subregion is what we're going to give rise to, not just the causal wedge, but it's going to give you actually the completion of all that, because it does not necessarily need to be a one particular region. So it will be in the end the integral wedge of boundary subregion, which is causally complete, and will have a naturally associated von Neumann algebra in therein. So while we are going to then associate all the operator algebras of the bulk and the boundary separately, we want to address in a generic setting where the Hilbert space of the theories are really infinite dimensional. And of course, it can be working in the finite dimension as well. It's just limiting a particular type of von Neumann algebra to be of type 1. So then you should probably ask, why am I caring about the infinite dimensional perspective here? And why is that really the case? That's because we have quantum field theories that's always going to be satisfying the Ricci-Leiden theorem from the Whiteman axiom, that for any bounded region A, by acting on a vacuum, that's going to be known as omega, with operators associated in that very region, we're supposed to be able to produce a set of full states, which is dense in the full Hilbert space of the quantum field theory. What it in practice means is that I can excite something here, and you'll be able to see it across the globe. And that's possible if it's not quantum mechanics, it's quantum field theory. So we have fields that's going through, I mean, it's decaying in the end, but it goes through infinitely and far away. So that if we put the really high perturbation onto a very little function over there, then it's going to still create the effect. And that's like the nature of why quantum field theory is different from quantum mechanics. So in turn, if you want to understand these features more accurately, it's really important to address the settings where we can understand what the infinite dimensional Hilbert space is. And of course, this means that you're not really regulating any quantum field theory explicitly. So we're going to try to understand in that context how we can get the holographic understanding in that perspective. Yes.
What do you mean for reaching that? Does the theory have to be conquering variant? Or what is it?
That one is, I think, it has this locality by the Haag-Kessler. So that when you're having, let's see, you have two different causal regions and they have to commute. And then it has a closed Hilbert space that can be addressed. It does not need to be Poincare. Any normed space that supports algebra, that's the required assumption for this. Yeah. Of course. Of course.
So there exists this approximate sense. What can I find out?
Huh?
Where can I find out?
This is going back to the same question that I will really address it. I promise. I actually promise. This is actually a very good question. So, a Reed-Schleider theorem that outputs of that, if you notice in the statement, the only thing that needed to exist for sure is a vacuum. That's a state. So then how do we state that in in the operator algebra context that satisfy the Reed-Schleider theorem? It's given as a state that satisfies two different things. It has to be cyclic and separating. So one of the easiest way to define them is let's have a map between the algebra onto the Hilbert space where it is lying on. So the operators are in that Hilbert space. So that the map would be then the operator in there to act on a state onto that. So then this state particular is a cyclic with respect to this fundamental algebra if the Hilbert space is the closure of the image of the this map, meaning it is not quite surjective. So, and this is separating if the kernel of this map is empty. So in turn, just the map is complete injection, which makes sense because we need to have injectivity to have everything described, but not quite onto so that we don't preserve entire structure, the formalism, and microwave ways. So then Reed-Schleider theorem really says that a quantum field theory always has a cyclic and separating state with respect to von Neumann algebra. Now, this seemingly naive statement will be the main source of where a lot of things will work throughout the talk today. And the existence of this very vacuum will be how we're going to be able to prove and derive the new structures that we're going to find throughout the talk. So now let's put these together to really formulate the infinite dimensional holography. So this is the setup that I'm going to explicitly form it with. So let's say we have the boundary control field here. This will have a boundary operator that I'm going to call it as a physical operators. That's the O, and its complement will be the associated to the region that's the complement of the bar, that will be O primes. And this will be forming in the Hilbert space of the conformal field theory. So that will be called as H this. So this will be denoting everything on the boundary. Now, these will form von Neumann algebras by taking its bounded operator sets, and that will be associated to individual regions. To remember, it remembers the subregion where it's associated with M of U. So I'm going to notate them as MA, and for the complement, that will be identical to the commutant. And this is using a locality of the Haag-Kessler et al. Now we can do the same association in the bulk, so that we can have the bulk operators in region A that's associating with the entanglement wedge of this boundary capital A. I'm going to call that everything with the tilde as the operator. So tilde will be everything in the bulk, and non-tilde will be always in the boundary. I'll stick to this notation throughout the talk. And the prime is always a commutant, and this will be always the same throughout the talk as well. Now, these individually will also form von Neumann algebras by taking their bounded set of operators. And so that will be then denoted as M of small a and the small a prime. Or small a is now given as the entanglement wedge of the capital A. Then now we'll have an isometry as a holographic map that maps from the H code as that MA and the MA prime that we just defined lives on as a fault. And this map will have explicitly the existing cyclic and separating state. That's the one that was giving us a vacuum that Richelieu theorem gave us the existence. It doesn't have to be unique, but it just has to exist. And that will map under this isometry. And from this context, then we're going to be reformulating in this way to get the bulk reconstruction as the one that's copying from the bounded all these bounded operators that we can have on there, and would be generic operators that we're going to have to be mapping into the between the bulk boundary to bulk.
Perfect.
Yes.
Are you just going to use the fact that the isometry D exists, so there is a holographic map, or are you going to tell us things about the holographic map?
We're going to actually take as a isometry as a holographic map, and in the end, I'm going to even take that as a explicit some explicit map that is CD, completely bounded, so I can even break as a quantum channel to associate the operator to operator as an isometry, and I'm going to use that as the mainly for the holographic map here. But the rest will be really addressed by the von Neumann algebras. Now, in this context, what we know about before is that entanglement wedge reconstruction, that's the bulk of reconstruction within this entangled wedge, is exactly identical to the Ryu-Takayama surface, and also the relative entropy conservation between bulk and boundary up to the G equal to 0. And in here, what we really had to utilize in the known context of the Ryu-Takayama surface is really the limiting surface of the quantum extremal surface that defines the region of where the entangled wedge really lives on. And also in turn, then we can have the JLMS formula, so known as the entropy conservation, to be really exactly working, again, in the G equal to 0. And here we had to actually utilize the generalized entropy formula together. Now, in the infinite dimensional context, while Ryu-Takayama surface is really great, that will diverge, so it's very difficult to address it directly. However, as you remember, the von Neumann algebra's commutant is everything with commutant. So then the Ryu-Takayama surface that it finds is the center of this von Neumann algebra. Another way of saying that it's exactly the intersection between the von Neumann algebra and its commutant. So that by grabbing such a center is where the entangled wedge line, the extremal surface, really lives. And through this way, we can actually compute and understand where the entanglement wedge will be really looking like, in a way. Center of the von Neumann algebra.
There's an operator associated to Ryu-Takayama.
That's right. So this von Neumann algebra is on the open spacetime. It does not include the boundary, you notice. And that's also the same here. But the center is the one that's the intersection between its own and its commutant. And that's really the one dimension lower, it's 4-dimension one surface. And that's where the operator is defined with respect to there. Entropy. So we're gonna actually go through that. So that's a work in progress in a lot of ways. I think that it should be related to, in the end, some like this Jones index in the end, but today I'm going to actually address it by grabbing it through using generalized entropy to be defined in that particularly nice region to grab how that the formula will be living. I know. I don't exactly know the form of the operator will be exactly like. I mean, there will not be necessarily Hermitian, and there will be a Hermitian operation that should live in there but it's a center. So, yeah. I mean, the only thing I know is it has a geometric meaning associated. You can kind of see it and view it, but to describe it explicitly in full, no one has done it.
If M capital A and M capital A bar form say a type 3 out or something, then by definition it has the center has to be a trivial, right?
Correct.
Right. So then is the operator corresponding to the RT surface also just like density?
Well, if they're not necessarily type 3, it won't be, but it will be type 3, yes. It will be but trivial, but in what sense? Because ergodicity map is kind of not necessarily given. So it can be trivial with respect to what is a very important question, because it also has a smearing operator that's supported on it. So it's in a sense it's trivial, but not trivial in that way.
So is the expectation value of this operator the root that without the area?
Huh?
Is the expectation value of this operator the root that without the area?
Yes. That's that on that. That's 4-dimensional one surface.
So it's not necessarily entropy, right? I mean, it's just basically you're just
Yes, but how would you describe that as an algebra? Like as an operator, how does it really look like? It's a very difficult question to address. And we would love to know, right? So first thing that you really notice is the relative entropy that we have utilized in this down right bottom. If you want to really understand that these in the infinite dimensional context, as I was saying, the root check negative surface on its own as a formula cannot be really used, but the other two are still intact. Then the relative entropy needs to be then understood, and when we don't necessarily have the linear like a density matrix, the operator that we can have, because we would not necessarily even have a notion of trace. Right? If you remember in the very beginning when I was giving you the von Neumann algebra, trace only exists up to a type 2, not entirely. So we need to now understand how to generalize this in a perfectly coherent way that's going to give rise back to what we already know when you put it into the correct context. So when we were all in high school or undergrad, we learned this relative entropy as a trace rho log rho minus rho log sigma. It's a very naive, equation, yet it's so crude. If you look at it, it's kind of like a measure of distinguishability between this rho as a state generating and sigma as a state generating. So so this one now you need to go into a bit of Tomita-Takasaki theory to generalize this by taking what that measure really means, because you can define such a measure correctly at a given operator set, then you're good. So one way to do them is finding a relative modular operator. So when you have now two different states, psi and phi, one of them has to be the existing cyclic and separating state, the vacuum. Then with that, that's what you're going to really get the expectation value with. And this log of these modular operator, which is, by the way, identical to also the exponentiation of the modular Hamiltonian that really sources these flow in the operators, that can be grabbed by taking Tomita operators. That's the S is a Tomita operator, it's not an entropy. That's a LS. So that's the one that's really mapping from the operators to the conjugates. So through this context, then it can really map as paired by one another, and thus it really generates the modular flow together. And in that way, we can generate all of them as the same log format, and you can see that this will be really distinguishing different states. So when we put it back to the existing trace map, it exactly resorts back to the what we already have. So this is the direct generalization we're going to take to deal with the relative entropy throughout the talk. So the first thing that we're going to understand is when the this exact relation really work, where the entanglement reconstruction is exactly equivalent to the relative entropy conservation between bulk and boundary. That will be only the order of Newton to 0. So this is a theorem that we proved then using the von Neumann algebra. And the ingredients that I'm going to only use is the holographic map isometry between the Hilbert spaces, and how individually they'll form von Neumann algebras by their bounded operator sets with the regions that we just found. In fact, I'm going to use one very crucial assumption that's given by Reuter, that we have the vacuum as a cyclic and separating state, and this definitely exists for both the encode and this. So the code is a code subspace, so it's in the bulk, and physics is the boundary. This is how a theorem really looks like. Don't worry, I don't expect you to read it and have it off the top. I just wanted to point out that all the constructions and phrase as all the operators really mapping. The tilde, remember, is the bulk. Non-tilde is the bulk, boundary. And the relative entropy that we now defined in the Araki context to generalize will be expressly mapping to one another, and can show that they're equivalent. So this is, if you remember, this is how we really put it together in this context, so that we have the code as a code subspace. While the theorem is taken in general format, this is what ADS-CFT will really tell us, that we have a isometry between the Hilbert spaces, and then we can recreate the whole operators as long as there are these von Neumann algebras well defined and admitting individually cyclic and separating states. as a vacuum, and it maps to one another under this isometry. That was the really crucial information. It's actually very seemingly naive, but very strong as an assumption, because we are mapping from the vacuum of the boundary to vacuum of the bulk. Now I was slightly lying. I actually used one more assumption. If you look at it, that means a set of cyclic and separating states with respect to the encode is dense. It looks like there's one more assumption. It just means that now we have the full set that's acting on it as a vacuum is providing something with respect to in the box to be dense. Can we even relax that? Because that's like additional ingredients that we probably should not actually need. We can do it from the bulk reconstruction direction to the relative entropy, but not vice versa. That really then gave us a little proof that the validity of the two is not exactly equivalent, but in turn, bulk reconstruction is actually a little bit more strong to one another. This information will be more crucial when you're trying to go beyond to really deal with the approximate recovery, not the exact recovery. So thus far we have, yes.
So when you prove this, I guess there's a lot of linear algebra going in.
No. The von Neumann algebra is in generic, so it does not necessarily need the matrix, right?
Where does gravity go to?
So gravity here at the moment is just a quantum field theory. That's the semi-classical bulk, right? The thing that I used thus far is that there is a bulk Hilbert space as a code Hilbert space, and the operators can be addressed there. Just with the smearing function that will be differently formed of von Neumann algebra.
How is it fixed here?
So
I'm trying to figure out how much of this is algebraic and how much of it uses gravity.
so the full proof is using completely just algebraic things, but so the theorem on its own does not necessitate to have the holography in the understanding. But it's very crucial to remember that there is a map that's going from the between H code and H physics, and that direction. Yes.
But beyond that, it's algebraic.
And also the algebra is basically the sub-algebra because the Hilbert space is going from one to another under this isometry. It's isometry, so that's kind of guaranteed.
So what sense is the
So it's a holography for this particular context we put in this setting. Because if you remember, I crucially told you that the smearing function, remember the bulk operators will be express a boundary with the smearing functions, and they're already addressed inside the Hilbert space as all the operators, because operators are integrated over with those functions, and this is how we get the operators, and they're already part of what defines the Hilbert space. Now, of course, we can address that trajectory in a different context necessarily, but it will be a little bit more off-putting because, first of all, this isometric map would be not necessarily present in other type of duality, like AGT is not going to work, for example. And also because of it, the von Neumann algebra will be then having inclusion property because of this association. And that was, of course, done with a holography in mind, and that's what we want to understand as a physicist. But of course, like for that to be duality to work, I'm sure you can come up with something like that, but it's very hard.
So you said that you are working on some classical gravity. So what happens if you change the background?
So this is background fixed. When you're changing the background, it's a lot harder because now you're turning on other type of perturbation away. I'm going to be dealing with a non-perturbative in there, but I'm still fixing everything semi-classical. I mean, I would love to do that. I think it's really hard. Well, it's a relative entropy, so it's with respect relative. So just plain entropy is not a concept you can define in a generic type of context because of that reason. And that's why everything is not phrased relative. Now, thus far what we've achieved in one crude line is that we have an exact relation between entanglement reconstruction and relative entropy conservation in quantum algebra. And this is order of G Newton to 0. Remember that. Now that's really great algebraic theorem that, of course, I worked hard to prove it with a lot of math. But it'll be useless if you can't really come up with examples to it. I mean, you're a physicist overall. So So I constructed like a variety of possible tensor network models that can deal with it as like, so it's like a discrete version of understanding this taken to the continuum limit. And you can actually demonstrate that the entangled wedge reconstruction is satisfied and relative entropy conservation is satisfied, and thus the theorem is giving as an example in that context. So let me highlight one of the particular ones that's kind of easy enough to just visually see how that works. So this is the particularly simple tensor network model that took two Qtrit codes and glued together. And Qtrits are pretty nice, right? We just have Qtrit, like so that instead of bell pair, we have the Qtrit version of the bell pair. And then we can explicitly find the unitaries acting on the two Qtrit states under, and this is the isometry we'll find. So I and J is the bulk node, and this will be the boundary node in particular, is how we can think of it. But it just literally gives them person can write this explicit map. And then you can find as a reference state a maximally entangled state. And in this context, we can write the this following the last line down there. So the psi ij is on here. So that's the vector in the black Qtrits. And the one with tilde outside, that's the image under this isometry, right? It's from bulk to boundary. And then with the unitary operators acting on now these white Qtrits, we can write that explicit operation down and we can compute them. And what it really does is that this psi a tilde b tilde on the top there is the same as a state that we originally started with a psi ij on here, except on the Qtrits a tilde and d tilde. And what it really does in the end is that these unitary matrices are really then recovering the reference state and through that protocol to find the original the bulk psi ij state. So that from the boundary configuration, we recovered the entire information of the states that we find in the bulk black Qtrits. So then we can define operators with respect to these. So we can find the operator acting on the Qtrits here, and then you can find the utilities in this format. It's harder because remember it has smearing content, so it requires a bit more procedures. So those are the ones that's going to have explicit utilities, and from here, with a lot, we can compute explicitly the star algebra that's going to be the acting on these operators, and then that on the finite number of Qtrits, and now taking the completion with the reference state to get the full infinite dimensional Hilbert space and its associated infinite dimensional Hilbert space by taking the closure. Now, these are not generically bounded, right? These are generically unbounded operators. And to get the von Neumann algebra, an easy way to compute them, or not necessarily easy at all, is to compute the double commutant, which is also known as the time-Taubes theorem. But also here, it was just a definition, right? If it's a star algebra, the double commutant maps back to itself is a von Neumann algebra. So by taking the commutant and the double commutant, we'll be able to compute such von Neumann algebra, which this is a particular one that we juxtapose all of them continuously, and we can find explicitly the von Neumann algebras and write them very accurately with full entire operators and all that. And we can write down not just the explicit operators of the Qtrits, but and algebras, but unitaries and isometry, and then every information that you can find in this toy model. Now that's great, but this is a particularly very easy model, just one-dimensional up and bottom. And it's super particularly nice. I mean, it just sets the positions of all those. It's not really like a simple, it's like a little better version of the lattice individually, but a little more, but not much more beyond. What I'm really trying to say is that computing the double commutant is really difficult in general to do. So what if it's really then impossible to construct those explicit double commutants in general? Then we're having very difficulty to compute the von Neumann algebras and the theorem is lost. So we cannot really understand how that's going to work as a bulk reconstruction and the relative entropy conservation in general. In fact, then this will be very difficult to do. So we should then modify it in a way that it does not quite need to have the von Neumann algebras, but you can just work and just directly operator pushing type of formalism with just less information in the von Neumann algebra. And we have done that. So what we're going to really do is we're going to now find a way to not necessarily directly provide the von Neumann algebra at first, but we just have operators like in the happy code or Mera or many other tensor network you're familiar with. By taking some algebra of operators, by taking the set of all the operations that we have with the operators, and without taking anything, and we can just find a procedure to do it in a way that we don't have to explicitly find the von Neumann algebra. And I'm going to call this operator pushing because really what the tensor network model does, it just pushes out the operators. So then we're going to start with just a star algebra with the operations on them. Its explicit name is for use is C star algebra. And from here, we're going to have a KMS state. KMS state is kind of like a cyclic and separating-ish nature for C star algebra. So that it's kind of like a vacuum-ish on this less version of the algebra. So we just have the any tensor network or any discrete or lattice model, we can just work with those forming as an algebra. So we can have then the isometry of that level between block and boundary, and that's all we have. So that's that, and you can associate the pullback of the state, which will be associated onto the one in the bulk. And there's this procedure called GNS representation or GNS construction. And this, what it does is it's really taking the minimal possible Hilbert space. The C star algebra doesn't really have the Hilbert space. And so address it so that we can get the C star algebra with the minimal Hilbert space, with the norm and everything confined, so that in turn, at a given good setting, it generates a von Neumann algebra. This von Neumann algebra always has associated Hilbert space, but not necessarily the easiest route to do. But in this context, it is actually possible. And in turn, the reason why it really works is that we have the KMS state and it's pullback. So those will map to actually C star algebra with the corresponding Hilbert space with the now thermalized state that is explicitly cyclic and separating in with the C star algebra. And in turn, from here, we can get the von Neumann algebra. So we find in the right is that we created the von Neumann algebra in the bulk and the boundary, and it has the this isomorphism that I've been keep using the word U, and it's guaranteed by having the pullback of the KMS state as well. So we recreate the whole setup that necessarily needed to the previous theorem by just having a pure, not much relation. Whereas this, if you remember, the toy model that I used really needed all the state description to find operators. But the benefit of using this is that you don't really need to find the state. This operator on its own from like any tensor network model that's going to give you, that's on its own. It's just usable and directly applicable. So we can extend to much more upon error correcting codes. Like, for example, I've done it for the happy code, and it's an infinite dimensional analog of the happy code, which just grows continuously all the way continuously, so that it's going to really fill the whole hyperbolic disk, the Cauchy slice of the ADS3. Yes.
I recall my functional correctly. GNS representation means three things. You need the cyclic vector, which you have. You need the kernel of the map to 0, which you have. And you need a one-parameter family of homomorphisms.
Yes, we will have it. Yes.
Can I? Okay.
Maybe this will help you.
Oh, Jesus Christ.
Don't read it. Don't read it. But I can tell you. I can pinpoint you where that is. I'm only flashing it to you how difficult it is. Don't worry. I don't actually expect you to read this, but it's mathematical phrase very rigorously. I had to do really 10 times more math than the first theorem. This is very rigorously done, and you can actually prove all that in pure algebraic manner.
So, sigma I is one parameter.
Correct. Correct.
Can you point? I can't read one. Where's sigma I?
Okay, I will give you I'll give you the paper and explain you a brief moment, but let me move on for now. There are enough physicists in the room. So important thing. So by applying these, we could actually study the analog of the happy code and compute them very explicitly. Some of which that I want to really highlight just the result of is that I can show that entanglement wedge reconstruction works. Relative entropy conservation also works. Power law decay and correlation can be computed through this protocol. And I can find the geodesics as the Utah-Kennedy surface that works for the power law decay and correlations in the boundary to provide into those, and I can find the path, and all those things are doable by using these algebraic methods. And that's the magical theorem. Yes.
Type 1.
No, it's actually type 2.
Type 1.
Yes. And if you tilt the reference state, it can generate also type 2 infinity. But it's not going to give you type 1, actually. You can actually prove that it'll never give type. You will get type 3 if you do it in like some way, but type 1 is particularly not grabbable. I also find it very interesting. I think it's because that everything is so filled, and type 1 infinity might only happen when you have a small black hole further back, and that's going to remove the some of the pentagons, right? So I think by construction, since I didn't remove any of them, that's why I think it doesn't give you type 1.
Maybe that naive expectation would be type 1.
Yeah, it's very interesting. Yeah, I think it's like one of the first very interesting results that we find. And also the power law decay. As far as I'm concerned, the tensor network to give that very explicit to be computed doesn't exist beyond this.
Is there a reason why your one parameter family gets uplifted to one parameter group here?
Yes, if you actually read the proof, I can give you the highlight. Let's not do it now. I promise you, I'll actually give you them. I just don't want to derail all my 90 minutes. But yes, this is actually very doable. I mean, showing that I actually needed the net structure and compute it there. So I'm hiding a lot of math here. So what we have achieved is now we could do this for Neumann algebra or even C-star, like when you don't really have the Neumann algebra necessarily, and we can have all sorts of toy models. I know I didn't really give you a toy model with happy code, but that itself will take an hour, so forgive me for it. If you're curious, I will tell you. But you can actually use this as a powerful technique, and we can even use a lot of discrete model computations and all that. But remember, as I keep emphasizing, this is only true the order of G Newton to 0. What does it mean by really doing a gravity understanding if it's G Newton to 0? That's not really great. And this is really going back to Roberto. Yes, I'm terrible with pronunciation. Question, and that's really addressed it. What would happen when you just have a higher order of G Newton to 0 so that we can really understand something to be called as gravity theory? Because continuously, it's really the raising concern is that what does it mean by it's a bulk gravity theory? So we're going to then utilize a reconstruction wedge instead of an entanglement wedge in this context, because we know for a fact that it's going to be not addressing the jumping of the entanglement wedge profiles. And this is like philosophically really fun for the finite dimensional context, but of course it'll be completely rephrased in this particular more generic context. And also don't forget that there are lots of limitations to this exact theorem, in the sense that because the redundancy in the bulk boundary encoding that we have as holographic map can only be really consistent with the Ricci-Leiter theorem of the boundary. So the entangled wedge reconstruction is approximate, meaning it has additional higher order correction, and so it has an error dissipating. Then that's going to be the one that's corresponding as non-perturbative in G Newton is what is predicted. So the meaning it's non-perturbative is exponential to something divided by G Newton. And for state independent recovery, which is the formulas that we've been keep doing, if you notice, the entangled wedge did not have associated state particularly, other than the vacuum. In an approximate setting, in this context, a local bulk operator has to be in the explicit and the entangled wedge of all pure and mixed states corresponding to the boundary region. And when I see mixed states, what you do is you purify it, because we don't know how to deal with the mixed states directly. And then what it really means that depending on the state, the entangled wedge depends on it. So by changing them around, it'll jump around. So this is how you're going to deal with the reconstruction wedge, but we need to build this profile in the algebraic context, which I'll highlight very soon. And because of the presence of these non-perturbative errors in the bulk reconstruction, it is very crucial to really understand the holographic calculations of a page curve that will have explicit correlations onto them. And that's going to affect our relative entropy conservation part. So then let's phrase everything as a quantum channel as an encoding, because the earlier setup, well, that's very nice. It's a lot harder to deal with it here. So I'm going to now take quantum channel is such a fancy schmancy name, but it's just a normal unital completely positive map. It's nothing more than that. And then we're going to keep the same protocol. So we're going to have from the boundary of capital A, that's going to map to the other boundary set of operators in the bulk. So it's the H code. And that's the same V. So I'm keeping the same V as a isometry, literally. And you can have the same thing for the complement. So that's going to be the complementary quantum channel. So in the very explicit exact setting, these maps composed with the recovery channels that we're going to have here correspond to exactly the holographic conditional expectation is the word that I'm going to use. Let me define what that means. It's a positive map that really keeps the identity, and then it does really the partial trace thing out degrees of freedom. So when you're acting on all of them, it can just be keeping it there and take it out. So it's like a partial trace, but because we don't really have trace, this is the one that's working for more generic settings here. And non-perturbed gravity is very important, especially when there's an existence of a small black hole, for example. It does not necessarily need to be, but it does. So that imagine that I just put that nice black, there's some small black hole, that entanglement containing that, and that part is not state dependent, state independently recoverable. So this is where like the easiest setting you can find where reconstruction wedge is very necessary. So from in this context, approximate reconstruction is now finding a reconstruction wedge, the maximum possible region that is completely reconstructible with respect to then state independent waves. So how we're going to find them is really the intersection of all the entanglement wedges we find with respect to all the mixed states we can write in the code subspace. So that this will be the one that's really containing the higher order of the G-Newton in a non-perturbative manner. So in order to do them, as I was telling you, as I see mixed state, I need to purify. I don't know how to really deal with it. So we're going to do the purification. So the difficulty here is that now from here, we have the regular H code, and then it's like a thermal field double type of setting, but it's more generic because you cannot just do that. So we're doubling the Hilbert space. But don't forget, what does it mean by doubling the infinite dimensional Hilbert space? That's not really possible. So you can have the finite version of the copy that you're going to have as an H code star. So we can extend the quantum channels we had, and also the complementary channel, so that it keeps the same encoding of the information by coupling with the identity over it. So that in the end, what that really does is it's going to give us the boundary algebra that we had, MA and MA prime, and additional information in the auxiliary system here. The bounded set of operators that can live on this H code star is tagging along together. So think of it like it's a reference Hilbert space that can be used to encode lots of information and then coming back out. It's like additional of this is very important so that we can deal with the additional corrections that we need to have. So that what it really does is that so this is the same technique of the GNS representation here, and it's for done for the any spaceful normal state, and that can live in the original bulk, which was the bounded operator of the H code, into now purified into now the full doubled copy of the H code and the H code star together.
The H code is the space bounded operators.
The bounded operator set can live in the code Hilbert space.
When you say state on space bounded operators, what's that mean?
The state based on those that can live on those operator set that can provide on by the state operator correspondence. State is acting on those operators. So now from here, individually these complementary channels will give rise to an associated entanglement wedge phenomenon algebra, so that this will be living on the W is a new state because it's state dependent. The entanglement of the A is not necessarily now unique because of the mixed state, and it's depending on the state together. And they're going to now live along with the additional auxiliary system we have to really think about. So from in this context, then we can take all the intersections that we find with respect to all possible degenerations in the state, and that will be the intersection we're going to find with respect.
Yeah. So what's the input?
The input here.
Yeah, what's
So the
output also?
So I am explaining that what we're actually going to deal with it. The input would be actually like a very in the theorem format. It's probably what you're asking.
It is the
Mm-hmm.
So let's say I know lots about CFT and I know lots about above.
Okay.
What do I get from above?
So what we were really finding is that we're taking from originally the bulk reconstruction and relative entropy to be exactly equivalent, but now we're going to have supposed to be not exactly equivalent. So we call it complete approximate, a complete recovery. Now it's an approximate recovery. And the amount of that's going to be covered is bounded by non-perturbative gravity corrections that we're going to have. And then we're now having this protocol to have it so that non-perturbative, the error from the relative entropy is not quite conservation, corresponding to how much of the dissipation that we're losing from the bulk reconstruction and vice versa. Yeah, it's exponential, yeah, negative divided by zero. Yeah.
And it's relative, but you're keeping, what is the computing exactly? Sorry.
The bulk is the one that's what really demonstrating here is this is the not entangled wedge. So entangled wedge is no longer state independent because it depends on the state and it jumps around. So we are now taking the reconstruction wedge when we have the this non-perturbative error present, and what is the minimal region that can be reconstructible under the state independent recovery. So we're taking the intersection over all the states that we're allowed to have. And this is the minimum region that's confined that's still state independent wise reconstructible. So it'll be a bulk reconstruction in this reconstruction wedge. So I'm kind of dealing with this zone that's kind of like in between.
And you're taking some theory when you compute with exactly the bulk, and then you know that's why you know that your result is not the exact result up to e to minus 1.
Yes. Yes.
So what's the theory?
What's the theory? So the ones that can have like small black holes will be like that. So the ones with a very high conformal dimensions from the boundary, like for example, like strongly correlated like theories that can have like n=2 for the theories, for example, like those will have very high conformal primaries.
Small black hole, the scale of the size of the black hole is small compared to
Size of the black hole is small.
Yeah, microscopic.
All right. So then now we have the reconstruction wedge satisfied. So that now we really like distinguishing this original, like original wedge that jumps around and this new, it's like having two men's zone. I don't know. Maybe that's a way to put it. So now we have done reconstruction wedge algebra as this now M of small a. So I'm sticking to the same notation. So that will be what we're going to explicitly find. So in this context, in approximate setting, what we're finding is still the this mapping and onto the complement mapping. And if you notice now the black holes on this side, it's of course easier to deal with the complement side rather than the regular side. So how you're going to access this is through the complement recovery. So then you should probably ask, why did we need such this complicated setup? It's so hard to get a wraparound of auxiliary system with the reference state, and it's so complicated and all. It's because we want to really address everything into the diamond norm, or also known as completely bounded norm. And that's very difficult to deal with it in a generic infinite dimensional von Neumann algebra, which is very different from just matrices that we can really use. So we're really paying a cost a lot here, and by having a rather very complicated setup for the reference system, which is also its benefit because this is how we actually define the correct reconstructing wedge zone as well. And this is really giving rise to a format that is compatible to really give a ground to work with a completely bounded norm in the end. And it's explicitly different from the Trold-Petzmat approach. In fact, Trold-Petzmat approach will never be able to admit such a reference state, and it would not be really working with the context where it has their non-gravity errors. It's fundamentally not really feasible. And this is very similar to having information disturbance trade-off. It's just that information disturbance trade-off doesn't work in infinite dimensional Hilbert spaces. So what we're really going to use is something that's very similar to information disturbance trade-off. It's called privacy correctability duality that is shown to work in most generic contexts. And we're going to use complementary recovery to now attack this explicit profile. So where we left off was that we just had the reconstruction wedge algebra to be done. And we're going to use, if you remember, conditional expectation. That's really just a partial filling out the degree of freedom. So here we're going to take that explicitly, and this is going to give you a really big restriction, and that's really because you're allowing non-gravity, a non-perturbative gravity correction. So this can only exist if you can compute this MA prime as complementary region to be purely atomic. It's like atomically built as one. So we can have only a type 1 or a product of type 1 factors as a code subspace. Now, does it really intrinsically limit a particular thing? Not necessarily, because it's a code subspace. We don't really know about the full matching of the Hilbert space of the full bulk, but as a code subspace, that's saying a lot. Meaning it has to be atomically really buildable, so that whether it has to have a type 1 affinity or many products of type 1s, they can map to type 2, but fundamentally type 3 is inherently difficult. So which now goes back to nice comment that in gravity, what does it mean to really have continuous spectrum? It's inherently not possible, and it's what also algebra is outputting. So I think it's really matching of the same understanding. It's kind of good to understand then how to write this, and of course that push to larger limit can actually give more generic things, but on its own is very inherently not possible to get type. Now, from in this context, we're going to take a state that's a normal state on now this augmented system. Then you're going to take the state under the complementary channel, which is how I'm going to do a complementary coverage. So that's going to have not just the boundary complement algebra, but additional auxiliary system. You have to always trace the degree of freedom with. So from in this context, let's write the relative entropy conservation, which I'm going to call it as a modified LMS formula or modified quantum extremal surface formula. So the first, I know it's very complicated. I don't expect you to actually be able to read it. Let me explain the gist. The first term is clearly the original relative entropy term with respect to the complementary channel on the regular states. The second term is the one that's now mapping onto it, so it's the boundary and the bulk. And the next two are the generalized entropy of giving rise to from this state, and then the state that's restricted onto this A prime region, so that we're dealing with both generalized entropy and then the original relative entropy together. And that is bounded by approximate, right? By epsilon. Epsilon is the non-perturbative small entropy. So that will be the one that's giving us exponential something negative divided by 2. Now, if you look at it, this is the entangled wedge of the boundary region of the complement, and including this reference system. Those are the states that we're going to deal with. So then, but then the bulk region, this complement like prime, is the complement of the reconstruction wedge in all pure and mixed states of this capital A. So no matter how we choose, this is always contained within the complement A prime and the union reference system that we augmented with. So then on its own, this is always a 0. So relative entropy cannot have a non-vanishing constant. So that goes away. That's much smaller. Now let's look at these two generalized entropies for these two different states that we're dealing with. Now, if you remember, this state rho was the normal state in the full system, and then this was the other system, and then that's the reason why they were coinciding with what I was just pointing it out, because they will be coinciding entirely on all the entangled wedges for all possible states, whatever we choose. So they give rise to the same quantum extremal surface, and another way of saying that it's going to give the exactly same algebraic center, but thus it goes away, and these two will cancel out explicitly. So what we're left with from that very complicated setup earlier is just one term that you're going to have as a nice formula from the approximate relative entropy conservation. So applying this particular thing called Pinker's inequality, we can find this particular format, and this is true with respect to all normal states we will find. Remember, rho was an all normal state in the augmented system. So what we find in the end is just this simple thing. So it's encoding in the complementary channel, so the complementary recovery, and this is the thing that we're going to find. Now, here's the place that we're going to use privacy correctability. That's the generalized version of a information disturbance trade-off. So what is privacy? Privacy of a quantum channel is saying that if it's completely private, none of the information it contains is really accessible from the domain of the quantum channel. So that we can explicitly say that all the things that's private, that's what we're only seeing in the commute and not the actual one inside. So it's completely private. So in the earlier setup, what we had here this is going to be completely private in the exact setting. So that what it really entails is that the bulk algebra A and MA here is private with respect to the complement of the capital A for the usual boundary to the bulk map. So in the approximate setting, we're going to now take A as a reconstruction wedge, not the entanglement wedge instead. And we're going to have it dissipating because remember it had the air. So to address the air, we're going to call that epsilon. And then we can have an epsilon privacy, meaning it's not quite private, that the epsilon amount can dissipate around, and that's accessible from the domain of the quantum channel. So then on its own, it's going to have epsilon level of the privacy. So what is correctability, which is exactly the opposite concept? That means if it's correctable, that means everything is correctable from the commutative, which makes sense because it was completely private. So in the ADS CFT, the exact setting was telling you that exactly the same wording as that the entangled wedge of this region corresponds to the existence of the star homomorphism between the two phenomenon. And that would exactly be the complete encoding. And in the approximate setting, what it means is that you're going to now have epsilon level to be not quite correctable, so that, or it's bounded by that epsilon. So in this sense, it's like you can see that it's like information and disturbance trade-off in the same sense as like now a privacy and correctability correspondence, and this works in any type of phenomenon. The 1, 2, 3, it does not matter. So that if this is private, complement is 2 square root of epsilon correctable. Now, if it has epsilon correctable, it's 8 square root of epsilon correctable. So if you repeat that, it's going to be a lot less. But it always will. Now, this seemingly very naive statement is always applicable to any generic context. So that's another way of saying there's an information disturbance trade-off, something like that. The concept is very innate to having something like a well-defined map of some form of morphism level. So let's apply to where we have achieved. So we have achieved thus far till here. So if you look at that, we know quantum channels are always inherently completely bounded by definition. So you can take it simply as just that. Now, if you look at just that formula and apply to the definition of the privacy, that MA prime is private for this quantum channel, and thus it's exactly going to be the square root of 2 epsilon on the right side. That's the privacy that it gives. And then now we apply that to get the complementary recovery of the correctability form, so that we will now get the 1/4 root of 2 epsilon now. So we have the approximate recovery. So as a summary, what we really find is that we start with this relative entropy as a quantum extremal formula as a approximately conserved and dissipated away by epsilon. That was the non-perturbative gravity corrections. And that is equivalent to the approximate, with the approximate recovery for the reconstruction wedge reconstruction. And it's kind of awful, reconstruction wedge and reconstruction, but I didn't come up with the name either. So for that, now, if you look at it, it's 1/4. It's very peculiar. If you see 1/4, you should be like, if you put it in this format, it becomes a 4G Newton. So it looks like it's changing the area operator. It's how it really looks like in the relative and the entropy format. So it's kind of interesting in the sense that if we created a small black hole, that's also changing like a area. So it kind of matches with our intuitions in physics. But nevertheless, this is really saying that this is what's more, this is more restrictive than the other. If you remember earlier from the completely exact, what I started with the very first theorem that I proved was that this was much more restrictive side than the relative conservation side. And then I was able to relax this condition only one way for the cyclicity. It's like the same thing. This is much more restrictive. And we're actually seeing that explicitly. So it has several implications that and systems we can work with as applied further. The setup really crucially require the extra reference system, remember, the augmented finite version encodes star. The entanglement wedge of this on its own is very non-trivial, which will significantly change your description of the bulk construction, and it's a worthwhile thing to probably analyze further to understand them. And this auxiliary system can be really identified with, not always, but with the space of semi-classical states of Hawking radiation, or the space of semi-classical states of another boundary, so that we can really have the identification between the thermophiles double states. And we've analyzed them to understand, for example, demonstrate how state-independent recovery is not possible in the black holes, or going more explicit understandings of what we can do with these contexts. And thus far, we've been doing everything in like just causally complete space-time, so we can use kind of like in the course of life. So it's in reality causally complete. But we cannot actually really address the geometric description, how it really looks like for the entangled wedge or the reconstruction wedge. So how it really like forms and how we can explicitly understand where the centers or maybe all the other things can really live, the boundary. Then can you really apply these privacy correctability duality setup in the exact settings? Now with the additional flow, not just the modular flow, but the Kang's co-cycle flow, to really now see the entanglement wedge. Because there was a paper by Busso, and Shabazi Mugadam, saying that about how this is really coming from the kink transform, and then computed a lot of GR computations to see that the Kang's co-cycle flow can be generating such a format. So from this context, it would be very interesting to apply this in algebraic sense to see how that would work with the conserved relative quantity or approximate conserved relative entropy quantity, and to visibly really describe where that really comes from. And using that together is currently almost done, but just in case some of the little math things are wrong, I'm not going to present it necessarily today. But hopefully, if things will have on, you're putting it together as an intertwining of the kink transform and the Kang's co-cycle flow, and proving this with an operator algebra person, actual mathematician, because myself alone would have been very difficult to prove this. And hopefully it'll come out in December. So in short, let me summarize all the things that we've done. I first showed the exact relation in the infinite dimensional Hilbert space context, so that entangled wedge reconstruction and relative entropy conservation between bulk and boundary are exactly equivalent. And then that one was giving you in the order of G nu. We extended that to the setting where fundamental algebra itself is very not acquirable easily, because taking the double commutative to actual construction of the fundamental algebra is very limited in most settings, so it can apply to a variety of different other code models. Now we could do non-perturbative gravity corrections by addressing that as an approximate recovery with the this error term that contains as an exponential to negative Newton. And we consider that and construct a reconstruction wedge. And in this context, we needed the augmented system as a reference system. It's kind of like also containing the Hawking radiations and variety of others. And we explicitly show that such is possible through complementary recovery. And for that, we actually addressed it still in the sense that when this reconstruction wedge can be visible, and how much of that is still preserved under this context. And the difference was having this 1/4 order of the error, which was very seemingly weird number. And we extended this, hopefully will come out soon. I just sketched a few ideas where it was coming from to take it beyond to the space-time to see the entangled wedge with the conservative relative entropy with the Kang's co-cycle flow, and hopefully we'll be able to detect with the more explicit curvature changes and the kinks associated with the algebraic context, so that we can really now visibly see geometric region where it really lives when it's non-trivial. Throughout this context, we established a lot of dictionaries between the two, so that now without proving much more things, you can just address them in the correct languages and you can just use them, and as a toolkit, a lot of things are already not explicitly done. So that we don't have to necessarily always prove new theorems and just use in the tool model and compute it explicitly. And there are many more applicable settings that has been worked out or currently work in progress. So for example, the baby universes settings could have been explicitly addressed with this algebraic framework and holography. And it could analyze as a Hilbert space on its own and can address the baby universe hypothesis and its reconstructions. And we could consider many variety of tensor network models, for example, like the notably infinite dimensional analog of the happy code. And we are working, hopefully this will go out soon, but I'll talk about it next week in the workshop on constructing space-time tensor network. So we're going to have an explicit discrete model of the space-time and compute their non-trivial behaviors in holography. And we can also address the time band in the boundary, which will associate to the hole in the bulk space-time. So it gives a meaning of differential relative entropy or differential entropy in this more explicit understandings, how it can be more generalized further beyond, and many more others. Thanks for listening. I'll be happy to answer any questions you have.
Questions?
So we consider the baby universe algebra, and coming from there, how we can, when the purity and the state constraint is possible, and what that results in, and its dual space or the Hilbert space, and overall, when is that matching with the gravitational path integral descriptions. And also we explain in this context how miraculous cancellation that we have is directly just a consequence of this algebraic framework. Nothing miraculous actually happens to us. That's already a crude summary of what can happen, but those are